Okay, here we go. So we've got this warm up here, and if you are doing this from home, not well, you're all at home, but if you are not live with us here in class, then you should pause the video and try them and then check back. So everyone here has had some time. Good morning, Hazel. Glad you're here. So we're gonna look at these warm up problems together. On this first one, it looks like we're going to need to subtract 1 to isolate the logarithm. So we'll have log base 2 of x is equal to 2. And then we're going to rewrite that into an exponential, and it will be 2 squared is equal to x. 2 squared is 4 equals x. And let me know if you have questions along the way. I'll be happy to stop and answer those as best I can. We'll go to this one right over here next. We're going to subtract 1 to get the exponential part isolated. It's 2 to the x is equal to 2. You might be able to see what that has to equal, but it's log base 2 of 2 is equal to x. And if you put log base 2 of 2 into your calculator or the Desmos graphing calculator, it's 1 is equal to x. Good morning, Elizabeth. Glad you're here with us. We're working on this warm up here. Moving on down to this next logarithm. We have a log base 5 of x plus 1 is equal to 3. So that's 5 to the third is equal to x plus 1. 5 to the third, 5 times 5 is 25, times 5 is 125, is equal to x plus 1. Subtracting 1 from both sides, we get 124 is equal to x. Questions on any of those so far? All right, looking at this one right here, rewrite it in log form. Log base 5 of 25 is equal to x plus 1. If you put log base 5 of 25 into your calculator, you get 2 equals x plus 1. Subtracting 1 from both sides, you get 1 is equal to x. Have a couple challenge problems here. I don't have a lot of room here to do them, but we'll see what we can do. So what I see is that these are both log base 3, which means we're probably going to need to do some kind of a log property. So I'm going to rewrite those into log base 3 of, in the numerator, x plus 5, and in the denominator, x plus 1, and that equals 1. So that means 3 to the first power is equal to, we're rewriting this in exponential form, x plus 5 over x plus 1. So that says 3 is equal to x plus 5 over x plus 1. Now, lots of people feel kind of lost maybe when they get to a situation like this. And that's sort of understandable. It can be kind of confusing here. So the best thing usually to try to do is to get rid of the fraction by multiplying by the denominator. So here our denominator is x plus 1. So we're going to multiply by x plus 1 on both sides in order to get rid of that denominator. So distributing on the left, we have 3x plus 3 is equal to x plus 5. And now that looks like something that you can work with a little easier. I'm going to subtract x, and at the same time, I'm going to subtract 3. So I'm going to get all of my constants on the right-hand side and all of my x terms on the left-hand side. I'll have 2x is equal to 2. And dividing by 2, I will get x equals 1. That's pretty complicated. Not super easy. That's why it's a challenge problem. Now, you should see that there's a pretty strong relationship between that one and this next challenge one. So we're going to rewrite that as a log base 3 of 1 is equal to x plus 5 over x plus 1. Does anyone know what log base 3 of 1 is? What is log base 3 of 1? Ideas here. Well, we can pull up a Desmos graphing calculator, and I have one here. And under the functions, miscellaneous, log base 3 of 1, we can see that it is 0. So on the left-hand side there, we have 0. Whoops. 0 is equal to x plus 5 over x plus 1. Now, in order to get our x value by itself, again, we're going to multiply by the quantity x plus 1, our denominator. And when we do that, that whole left-hand side, this just remains 0. So we have 0 is equal to x plus 5. Subtracting 5 from both sides, we get negative 5 is equal to x, and that is our solution. Questions on any of those? All right, here we are. These are just refreshing your memory about the laws of logarithms. These over here, these are the laws of exponents that we know. And it's important to remember that, let's suppose that you have something that looks like, I'll give an example here. A to the 12, if you're given that a to the 12th power, you could rewrite it as a to the 5th times a to the 7th, or a to the 4th times a to the 8th. Okay, so you can go this way with it, or you can go that way with it. Doesn't matter. Okay, so you can break apart that exponent. So related to that is the example for the logarithms over here. If we have, let's go the other direction, log base a of 5 plus log base a of 7, that will equal log base a of 35. So notice that I took this side right here and moved to that side right there. So I wrote it kind of backwards. Questions about that log rule? Okay. The next one here, I'll give an example. So a to the ninth over a to the third is equal to the a to the 9 minus 3, which equals a to the 6th. So that's a way to rewrite that exponential expression. So here with the logarithm, I'm gonna start with log base a of 5. And I'm gonna do this in a way that might be kind of confusing. 5 is equal to 15 divided by 3. So we could rewrite this as log base a of 15 over 3. So I added this step in here, and then right here, this part, the logarithm, is this right here. But I can do from this step to there because 5 is equal to 15 divided by 3. And then that's log base a of 15 minus log base a of 3. Questions on that one? I'm going to do something similar on the next one for the exponentials. A to the 8th. Well, a to the 8th, that 8 is equal to 2 times 4. So this is a to the 2 times 4, which equals a to the 2 to the 4th power. It might also be worth noticing that if we just switched the order of these and did 4 times 2, then it also equals a to the 4th power squared. Either of those, they're equal to each other. And the logarithm relationship there. So if we have a log base a of x to the 4th, we could rewrite that as 4 times log base a of x. And something that I don't do that I used to do is write my L for logarithm in script so it doesn't look like a 1. But if you want to do that, you can. It's not a bad idea. Questions on those laws of logs? All right. We're going to take a break and we're going to move our bodies for 1 minute. If you're doing this video at home, you can do that now too. All right, moving on from here. Now we're going to rewrite these examples using logarithm laws. All right. So we're going to use those laws that we just talked about. Since we're adding these two logarithms with the same base, the base is 3 on both of them, that means we can combine them together into one logarithm with that same base. And then we take our two arguments, the x and the x plus 1, and we multiply them. So x times the quantity x plus 1. Then I can rewrite that by distributing the x log base 3 of x squared plus x. All right, so I'm going to continue on through these, and then we're going to have take another look at them. Sorry, this shouldn't be capitalized there on any of those. I think that it was a correction that the software made as these were being written. Sorry about that. All right, so first I'm going to look at these two logarithms right here. We're subtracting them. They have the same base. So that means that we can combine them. And then the first one here, that argument is the numerator. And the second one here, that argument is the denominator. Plus 7. And then we still have plus log base 4 of x. Now, again, whoops, I need to have base 4 there. Again, we have two logarithms with the same base 4. We're adding the two logarithms together. So that means that we multiply the arguments. So it's going to be log base 4 of x times y, or just xy, over y plus 7. And that's that one. Now this one's tricky, this third one here. Remember that when we are multiplying a number times a log, then that can come in and it becomes the exponent on the argument. So we can rewrite that log base 3 of x to the 4th plus, now we're going to do the same thing here. The 5 comes in and becomes the exponent on the argument. Log base 3 of y to the 5th. And finally, the same thing, that 6 becomes the exponent on the argument. The whole argument there is x plus 5. So log base 3 of x plus 5 to the 6th. And that is how we rewrite it for the first step. The second step, we're going to, because these two have the same base, we're going to combine them. It means we're going to multiply the arguments. So we have log base 3 of x to the 4th times y to the 5th minus log base 3 of x plus 5, that quantity raised to the 6th power. Now we can combine those two logarithms. Log base 3 of x to the 4th, y to the 5th over x plus 5 to the 6th. And that is that one. Are there any questions on those? Okay, now if I were going to check answers here, I'll show you what I would do. I would put them in Desmos. So I'm going to pull up a Desmos here. And Why don't I see what I want? Oh, huh. That's maybe why. Weird. All right. So I'm going to graph. So I'm going to pretend as if this first one that we were given is an equation that we're going to graph. So y is equal to, and I want to go in and select this log base, and I'm going to copy it because I'm going to be using it quite a bit. So log base 3 of x plus log base 3 of x plus 1. And you can see that's what it looks like right there. Okay. Could scoot it over, get a better look at it. Even zoom out a little bit. Now, I want to do this right-hand side. So we're going to graph that. Y is equal to log base 3 of x squared plus x. And look what happens. So if I don't show it, there's the red one, the original one. Now if I show it, the blue one is right on top of the red one, but also there's this side over here. Why? That seems like, well then, doesn't that say that this does not equal that? Well, they're equal as long as x is greater than 0, they're the same. But when x is less than, it looks like -1 there. When x is less than -1, there's a problem. So here is the deal. So if we go back to this, we can see that the original one, so it was in red here. Let me highlight our original one. That's the one that we graphed at first in red. Remember that we can't have an argument of 0 or anything that's negative. So when x is less than 0, this doesn't work. So x must be greater than or equal, no, just greater than 0. And that's what we saw when we looked at that graph. So if we just look at the red one, x has to be greater than 0. Okay. So, but if we come back and we look at this one, well, if x is greater than 0, then this is positive, and that's fine. If x is -1, this is 1. 1 minus 1 becomes 0. Okay, well, what if x is -2? Well, then this is -2 squared, which is 4. 4 minus 2 is +2. So if x is less than -1, then this side works just fine. So x can be less than -1, or x can be greater than 0. So that x is greater than 0, whoops, sorry, that x is greater than 0, that matches. But on this side, x can also be less than -1, and that doesn't match. So it only really works when x is greater than 0. And we can see that graphically right here. When x is less than -1, there's this part of the graph that exists that doesn't exist for the red graph. Questions on that? How's everybody doing out there? Are we okay? Are we following along? It's quiet, pretty quiet territory since Callan decided probably a dragon would be what she would go with. Give me a thumbs up if you're with me, or some kind of here or something. Shady, thank you. Thanks, Alina. Thanks, Lucy, Mackenzie, Landon, Lirit, Jacob, Ella, Callan, Sam, Jack, Eli. All right, all right. Just wanting to make sure. Sometimes it's yeah, I hear you, Elizabeth. Me too. It's kind of crickets out there, so uh sometimes it's hard. All right. On this next one, before we graph it, let's look at what we think will work. Well, this y value, we're going to take that as just a number. So let's assume that it's a positive number. That way, this part will work. If that y is anything other than a positive number, then this doesn't work, and we don't even have to worry about it. Here, as long as y is greater than -7, it works. So this one y has to be positive, and so this one has a less restrictive, y can be greater than -7. So it allows us to have some things that this one doesn't. Here, x has to be greater than 0. So I'm going to graph these just like I did before, and I'll make this one maybe red. We'll see. So we think x has to be greater than 0. And over here, well, what does x need to be? We're not so much worried about what y is because we're just going to assume that it's a positive number. But let's see, what must x be? Well, it looks like x has to be positive. Does anyone see anything that it could be that the other side couldn't? If x is 0, then then the argument's 0, and that doesn't work. If x is, it depends on what y is, I guess. No, I don't see anything other than x is greater than 0. But let's look at the graph. So I'm going to get rid of those first two, and here I'm going to do y is equal to log base 4. And we can make y be whatever we want. Let's make it 5 for no reason. Minus log base 4 of 5 plus 7. That's 12. Because right here it's a y plus 7. And I just decided that y was going to be 5. Plus log base 4 of x. And again, we can see that x can be greater than 0. Now, y is going to equal log base 4 of x times y. Well, y is 5, so that's 5x divided by 5 plus 7 is 12. And let's have a look there. Looks like that one is the same. So we were right to think that in both cases, x just had to be greater than 0. So going back here, over here, x must be greater than 0. In both cases, that's true. All right. On this next one, here, if x is negative, it's okay because x to the fourth will always be positive. But here, if x is negative, that doesn't work. So x cannot be negative in this equation. So x is greater than 0. So in the original equation right here, if we have a negative x, that doesn't work. But notice that as soon as we go to that, as soon as we rewrite it, it's a problem. Here, x has to be greater than negative 5. But that's less restrictive than this. So x must just be greater than 0. On this one, whoops, I don't have my other parentheses in there. Because this is always going to be positive, and as long as here, it doesn't matter what x is there either, it will always be positive because it's an even exponent. Whenever we have even exponents, it doesn't matter what we put in, it's always going to be positive. So this to me looks like x can be anything except 0. If x were 0, then the entire argument there is 0. So here, this looks like x not equal to 0. So let's go look at these. So I already put those in right here. So this is the, let me just get rid of these two. This is my first one. So as I said, x has to be greater than 0. Look at that. That's an interesting looking graph. It goes up and then it comes down, and then there's this other asymptote here. You probably haven't seen a graph like that before. Pretty interesting. And then this one, yeah, so those go right up close to x equals 0, and down something went wrong. Oh, that's because that's not what I meant to write. So this is supposed to be y is equal to log base 3. And I made y 5 in this case. So y was 5. I think. Oh, this should have been. No, I made y 7. Here it is right here. Y is 7. So this is going to be x to the fourth times 7 to the fifth divided by the quantity x plus 5 to the sixth. And so here, there's our original red function there. So the original one. But when we graph this, Now look, so this comes right down close to x gets close to 0 from the left, and x gets close to 0 from the right, but they'll never touch it. So if we zoom in down here close enough, wonder how close we have to go. Yeah, so we can start to see that the two graphs are moving away as we zoom in. We can see them moving away. But otherwise, to the right of 0, so x greater than 0, these two are the same. All right, so you can see that here, the more we have to have x greater than 0 because that's the more restrictive of the two. So here we couldn't allow x to be less than -1 because then the two things would not be equivalent. This and that wouldn't be equivalent. Here, these two are equivalent. And here, this just said x can't equal 0, but this one's more restrictive. X is greater than 0. So that's the one we have to go with. All right. So we are going to take another break here. Take 1 minute and move your body if you would, please. Okay, and we're back. So now this is going to be an opportunity for you to rewrite using log laws, and then you should check to see now what values are allowed for each of the two original and rewritten expressions. All right, so I'm going to give you guys like let's do about 3 minutes just to do the first one. I'll give you just 3 minutes. So if you're at home, pause and give the first one a shot. All right, on the first one here, we can think about what values of x are allowed. Here, x has to be greater than 5. And here, x has to be greater than -5. So the more restrictive is that x has to be greater than -5. So we can say that x, whoops, I'm going to do it in a different color there, x greater than -5. Now if we convert this, this will be log base 7 of the quantity x minus 5 times the quantity x plus 5. And in that case, when will the argument be greater than 0? Well, it looks to me like it's the same situation. If x is less than -5, then this will be negative, and when we multiply them, it'll be negative. But if this is negative and that's negative, then this whole thing will be positive. So, is there ever a time where they will both be negative? Well, let's see. If x is -10, this is -15, and this is -5. Oh yeah. All right. So if x is -6, this will be -11. This will be -1. All right. So x has to be, it can't be less than -5, but it can be, is that, well, over here, it could be less than -5. So over here, x could be less than -5. Am I thinking about that right? I think so. It couldn't, though, be between -5 and +5. So then the other one is, or x is greater than +5. So let's graph this and see if we have the right idea here. So y equals log base 7 of the quantity x minus 5 times the quantity x plus 5. So let's zoom in. Yeah, so it looks like I had the right idea. X could be less than -5. X could be greater than +5, but it can't be in between. So this one's pretty unusual. So x could be less than -5, or x could be greater than +5. So the only time that these are both true, so this side is true when x is greater than -5. Ooh, wait a second. Right here, x has to be greater than +5. So that's more restrictive. This should have been greater than +5. So that's what didn't make sense to me for a moment. So right here, these match up, but this part doesn't. So in our new um, in our new expression here, x must be greater than +5. All right. Questions? All right. Take 3 minutes and give the next one a shot. Okay, here we are coming back. So again, we're going to not worry so much about what y is here. It's just a number. We have to assume that y is greater than 5 here to make that bigger than 0. And here y has to be bigger than -3. So um, this is more restrictive. Y has to be bigger than 5. But we don't need to worry about it really. Okay. So rewriting this, we have log base 3 of the quantity y minus 5 times the quantity y plus 3, and then minus log base 3 of x. Rewriting that, we have log base 3 of, in the numerator, y minus 5 times the quantity y minus 5 times the quantity y plus 3 over x. So in the original one, we're just thinking about x. X has to be greater than 0. Because it can't, the argument of a logarithm cannot be negative or 0. Here, it's the same. So these two should be the same when we graph them. So let's have a look. So y equals log base 3 of, let's say y is 12. So we're going to say that this is 12 minus 5 is 7, plus log base 3 of 12 plus 3, that's 15, minus log base 3 of x. And so therefore it looks like. The other one, the rewritten form, log base 3 of, and then there's a numerator and a denominator, and in the numerator we have y minus 5 times the quantity, y plus 3. Oh, y was 15. So that's going to be 10 10 times 15 plus 3 is 18. And then we're dividing that by x. 15 minus 5. I made a mistake somewhere. Where is my mistake? And I know I made a mistake because it's not matching up perfectly. Anyone have an idea? Did I make it here somewhere? If y is 15, y minus 5 times y plus 3, so that would be 10 times 18 minus log base 3 of x. So 10 times 18. Ah, right here. We said that this was 10. There we go. Oh, 10 plus 13. Closer. No, it's 18. There. All right. So I just input it wrong. I'd not decided what y was going to be correctly and input it. Sorry about that. So this comes out to be right. X is greater than 0 for both of them. They're exactly the same. And this last one, I'm going to go through it just because we don't have a lot of time left. Sorry about that. So we have a log base 3 of the quantity x minus 5 squared. That 2 just becomes the exponent. Same with the 7 plus log base 3 of the quantity y minus 3 to the 7th minus log base 3 of the quantity x plus 5 to the 3rd. And we can rewrite that as log base 3. And I'm going to do this all in one step. So the argument, because we're adding those two logarithms together, those become the numerator in the fraction, and this becomes the denominator. So it'll be log base 3 of the quantity x minus 5 to squared times the quantity y minus 3 to the 7th over the quantity x plus 5 cubed. And what I can see, well, is that here, it doesn't matter what x is. This will be positive, so no restrictions there. Here, x has to be greater than negative 5. If it's negative 5, this will be 0. 0 to the 3rd is 0. That doesn't work. So here, x must be greater than negative 5. Over here, in the denominator, that same thing is true. But, yeah. So it looks to me like these should be identical. So let's graph them and see. So this is y equals 2 times log base 3 of x minus 5 plus 7 times log base 3 of, and I'm going to make y 15 again. So 15 minus 3 is 12, minus 3 times log base 3 of 3 to the x plus 5. All right, so we said x had to be greater than 5. Yep. Okay. Now we have y is equal to log base 3 of, and then in the numerator, it's going to be x minus 5 squared times 15 minus 3 is 12 to the 7th. And then that's going to be divided by the quantity x plus 5 to the 3rd. Oh, so here this shows that it's just x not equal to 5. So let's see. Or no. So this one is we can have values of x between 0 and 5 as well. Right, right. Because if x is like 2, this is positive because it's squared, and this is positive. Right. So in this form, x can be between -5 and +5 because this will always be positive. But from if it's like 0, this will also be positive. So it can go from -5 to +5. So this one, x has to be from greater than -5, but so x has to be greater than -5, but less than +5, or x can be greater than 5. And because this is not allowed, oh, also x cannot equal 5 here. X cannot equal 5. These are complicated. The graphing helps, folks. Make sure you're using the graphing to get some of these down. These are pretty complicated. So x has to be strictly greater than 5 is all that we can have is when we look at those graphs. And this should have been positive. All right, folks. So there's some practice. I'll put that in the chat.